And welcome to the first inaugural session of the Tortus AI Academy. My name is Dr. Dominic Pimenta. I'm the CEO and co-founder of Tortus. We're still letting a few people join, so I'm just going to get started super slowly and go through the slides, but you can stop looking at this. So the purpose of today's session, and we'll give you a bit of an overview of the whole series, is really about orientation. So for those of you who are interested in AI, this actually might be too simple a session. It's very much a fundamentals review of the very basics, and I mean the very basics. We're not going to get into anything too complicated. The overview of the series as a whole is sort of for NHS, C-suite, and digital leaders to better understand the AI landscape as a whole. And infrequently in our conversations now, as AI company talking to all sorts of leaders across the NHS, I think there's a real gap in keeping up, but also having to evaluate technologies which are new and haven't been evaluated before and there's no precedence for. So it really is to ground the fundamentals and to keep it super simple. We've got a bunch of polls, we've got a bunch of questions that we can be asking in the chat here, and we'll do a question and answer session at the very end of the session today. The program today, we'll run a session every 2 weeks, with the exception, obviously, 2 weeks from today is in fact Christmas. So what is AI today? And then the beginning of January, we'll look at evaluation of AI in healthcare. And then we'll start looking at some of the clinical risks in late January there on the 22nd. And we'll look at how to drive adoption and implementation, and we can share some of the lessons learned and also from some of the literature. And then the last session, mid-February, will be about the future of AI in the NHS and another Ask Anything session. So the goal here today is to learn how to buy AI for healthcare wisely. So I'll tell you what this is a computer science class. And I'd be the wrong person to be leading that if that was the case. It's a crash course in AI for healthcare leaders from concept to clinic. So we're really going to look at the very basics. So today we're going to cover basic terminology in AI, some foundational concepts, and also look at some practical live examples of AI today. We'll go through a bunch of explanations about how the models work, what the basic terms mean, but we won't dive into a tremendous amount of the finer detail. So specifically, what we will not cover, do not ask me about the maths of the models or the deeper technicals of how to build these models. That's beyond the scope of this. But what we will do is share some really good resources after the session of courses that people can do if they're super interested in learning how to do that. Similarly, we won't get into the deep philosophy of AI. We might touch on some of the ethics and the risks when we come to that session next month. But today, specifically, we're not going to dive into will AI replace us or anything like that. We also won't be looking at any specific workflows. We'll just look very generally at the field, what the various streams and sources mean, and what the various systems are useful for and what they're not useful for, and we'll keep it super light. And the other thing that we definitely won't dig into today, although we will cover that in quite a lot of detail, I think, in the following sessions on evaluation and clinical risk, is compliance, medical device status, the regulatory side, what we think of now and what we think of in the future. So with that in mind, let's make a start. So I think when we talk about AI, I really want to get right down to the fundamentals and set up some definitions from day dot that are useful when we're talking about practical deployment of artificial intelligence in healthcare. There probably, there's many definitions of these things in the academic world. But for the purposes of today's session, we're going to make some very simple definitions. Number one, intelligence is the ability to solve a problem. And that is indexed actually on the speed that you can solve that problem at and the complexity of that problem. So artificial intelligence then is essentially a machine that can solve problems. Now, to demonstrate this and also to check that the chat's working, I would like somebody to put into the chat as fast as they can the answer to this maths equation, 20 times 18. And see if there's any takers for that. Yeah, 360. Damn, okay, so you did a good job, so that's very good. Wow, a very responsive audience. This is awesome. Okay, so now what I'd like you all to do, and let's see how fast, what is this answer to this equation? And let's see how fast we can get to that equation. And I will wait a little bit because I appreciate it's either pre-lunch or post-lunch, so there's some brains that are working pretty slowly. Wow, Helen Russell. Okay, very good. 38745. People got some calculators out, I'm sure. But I think the point stands is that when we talk about intelligence, the complexity of the problem, the speed is a very natural way of assessing that. And also that our human brains are very good at certain types of problems. We are optimized for pattern recognition, for example. Our instincts are very much like, is that a tiger over there? Is it going to eat me? We are quite bad, and there's no way I could ever get that answer in my head, at calculation, for example, whereas machines are exceptionally good calculators. They're very poor at pattern recognition in the way that we do it. And I think that's a really important thing to recognize, that although artificial intelligence is a machine solving problems potentially in a humanistic way, it actually isn't as easy for certain problems as it is, and much easier for others. So it's about using the right tool at the right time. So we're just going to go through a bunch of definitions today, and we're going to keep it super light. So let's talk about some terms that you might hear. So one of the terms you might hear is narrow versus general AI. So narrow AI is easy to define. It solves one problem or very few problems. The classic example, and it always makes my presentations look better, is classifying cats. Now, you might not think that's a problem. That's very hard for human beings, but actually that's quite a difficult problem. It was one of the groundbreaking problems to demonstrate some of the AI capabilities about 10 or 15 years ago now, was classification of various images. And the classic example is there a cat in this picture or not? Here's a cat. I think actually that's not a real cat. It looks like a fake cat, but anyway, there's a cat. And that's an example of narrow AI, where the machine solves one problem. And the problem is there a cat here or is there not? Now, you can also extend that to general AI, and there's a lot of debate about where we are, but the fundamental definition means an AI model that can solve many, many, many problems. Some people say, we haven't reached that state yet, and it has to be a human capability. There's some other argument that says, for example, a language model can solve many different language problems. Does that count as general? It doesn't really matter, and certainly when we look in the practical deployment side, it doesn't matter at all, but it's useful to understand that as a terminology in the background. Okay, so you'll often hear terms used interchangeably in the AI space. So just for clarity, just want to take you through what it means for an AI model, an AI algorithm, AI training, because these are things that you'll hear all the time. And also there's some fundamentals of how to evaluate these models that we'll come on to later that really sort of require us to have a good metric and understanding of what those things mean. So when we talk about AI systems, we use the term model, and that is a pretty good term because it can be thought of as an internal representation of certain patterns that the model has learned that can help it to solve a problem. So typically when you're training a model, and there's lots of different ways of training, you'll use an algorithm. That's the way of training the model to take data and to put it into a series of what we call weights or parameters, which essentially just a huge calculator, and to have some sort of output. Now, when we talk about training, the way that these models are trained is we will have a data set that we know is true. I mean, this is one type of training, and I won't go super hard into other types, but this is an easy way to understand. And we'll talk about a worked example later. But when we're doing training, we need to know that the solution that comes out of the model, if it's correct or not. And when it's not correct, what we do is we say, okay, try again, change the model slightly, change the calculator slightly, put the same data back in, and see if you get an output. And we do this millions of times, round and round and round and round, changing the model, until we get the right model that produces a solution as good or as close as we think to the right answer as possible. And that's what we call machine learning. It's AI getting better at solving problems over time. So just with this definition, you now have a definition of a model, which is the fundamental system where data comes in and solution comes out. You have a definition of what we mean by AI. You have a definition of what we mean by training, and also what we mean by machine learning. Now, here's a good example, and we go back to cats because it's fun for cats. So here's some data, and we've labeled this already. So we use the term labels to annotate data so we know exactly what the truth is. And sometimes that's human label. There's other ways of doing training, but we'll stick to the simple stuff for today. So here's a cat. You can see it's a cat. Here's a pillow. That's not a cat. Here's another cat. That's a cat. Here's a cat. That's a cat. Here's a slipper. Not a cat. Now, again, I'm emphasizing that machines are quite bad at things that we find funny, but I do also like this thing because you can talk about slippers and cats, and it's a completely valid thing to do. So we put that into the model, and this is to represent the various sort of loops of training, what we call epochs, into the past, and eventually we get a model, and then we show it a picture of a cat, and it goes, this is a cat, and we go, okay, great, we've got a good model that knows that when we show it some new pictures of cats that it hasn't seen before, it can recognize that, in fact, is a cat. Now, this is super interesting, right? So like when we talk about what the model has learned, in theory, it's learned certain patterns or certain features of the training data here that allow it to identify cats that it hasn't seen before. So for example, I'm just hypothesizing the model sort of learns that cats have pointy ears, they're a bit furry, and they're generally all this sort of brown, greeny color, which I'm sure has a name and it escapes me at this moment, and that equals cat. Now, here's a problem that happens with data, and this is why data is so important when you're training AI models. Problem number one, there's not enough data. So for example, the model here has learned that cats look like this, but it's also learned that cats always stand up, and they stand up in a pretty similar pose. Now here we've shown it a picture of quite obvious cat. It's got pointy ears, it's about the right color, but it's lying down in a pose that the model hasn't seen before, so it classifies it as no cat. And this is a classic example of what we call underfitting. There was not enough data in the original model training data that we put in to understand that sometimes cats lie down, and that is a feature that we'd recognize. Now extract that into the healthcare space, for example. Say you were training a heart attack model to identify heart attacks, and you only trained it on middle-aged men who came in with ST-elevated myocardial infarctions, big heart attacks, major heart attacks. Actually, that model would then fail to recognize women, ethnic minorities, and actually non-ST-elevated myocardial infarctions. So I won't use the term minor heart attacks, very controversial for a cardiologist, but other types of heart attacks wouldn't be recognized. So it's really important when we're considering training models, the data that that model was trained on is diverse enough for the solution that we want to implement. And that's a key thing to understand when you're evaluating vendors. They want to use it, they want to tell you it's useful in this setting. What evidence have you got that it's trained to be capable in that setting? And that's actually a really hard question to answer. Here's another problem, and it's a bit of a more complicated problem. So we also have a problem called overfitting. Now, in this example, what's happened here is we've trained this model many, many more times than actually is appropriate. And we've trained it over and over again. So now, instead of learning the patterns, it's actually just memorized these specific pictures of cats that it was in its training data. And when it sees a picture of a cat that's not one of the pictures that it learned, it says this isn't a cat. And that's why data quality is also important, but also how the model was trained and how it was tested. And this is called overfitting. And you see that sometimes, funny enough, in lots of healthcare papers, where they've created a model that performs really well on data that it's seen before, but it doesn't what we call generalize. It doesn't work at all on new data. And in healthcare, this is really important because you'll also notice one important feature. All of these cats are that green brown color that sometimes cats are. Someone will tell me what that's called in, I think it's eggshell. But here's a white cat, and it doesn't recognize that cats can be white, and therefore it recognizes as no cat. And another really good example of this is your training data in diverse ethnic populations, for example. If it doesn't account for that in the input, it can bias it in the output. And understanding diversity is also really important when we talk about overfitting as well. Some more definitions then, and we'll keep with cats because that's a fun thing to talk about on a Wednesday lunchtime. Deterministic. Now, this is really important when we come on to large language models and some future tech, but just to explain what this means. Deterministic means when given the same input, the same output will always come out. like a calculator. And that's relatively easy for us to understand. Most AI models fundamentally are big statistical representations. They're big calculators. Put a bunch of numbers in, the same numbers always come out. So statistical models, prediction models, and some computer vision models are all deterministic. And that means that if you put the same input all day long, the same output will come out. Now, probabilistic is much harder to understand, but in that context makes it a little bit easier. But the model fundamentally has an element of randomness built in. It is a feature, it is not a bug. So sometimes a given input will often have slightly different outputs, and that's because it's a prediction algorithm. And again, offline, we can get into some real good resources to explain exactly why that happens, but it's a really important thing to understand that if you put the same data in to ChatGPT, for example, large language models are probabilistic, the randomness can be controlled, but it can't be eliminated. And that is a feature of the systems. And it's a really good feature to have when you're dealing with uncertainty, when you're dealing with human complexity. So language is a human complex situation, weather forecasting is another one, where you actually, some uncertainty in the system is actually quite useful. So large language models, when we come on to talk about this, vision language models, any speech to text transformer, which is based on AI as opposed to traditional, and we'll come to these definitions in a second, so don't worry too much about that. But they will all have an inherent element of randomness. And that's really important, again, when looking at evaluation and safety systems of these models in how that's accounted for. In a similar way as you and most of the people on this call are pretty experienced with diagnostic tests. They have an inherent error, specificity and sensitivity. How do you account for that error when you're doing tests in a high-risk environment like healthcare? And again, important to understand when evaluating systems. Okay, so all of that was very interesting, and I blew all through that really fast, and we can come there and I'll share these slides. Now what we'll do is we'll look at some specific types of AI that you may or may not have already come across. Try to use healthcare examples for the most part. So let's start with computer vision. So computer vision is very simply, here's an image. The AI model tends to break up that image into a bunch of numbers in some meaningful way, and then the output is usually some sort of classification task. So the classic example now, and actually I think this is technology that's live in the NHS, I've certainly seen it in a few different places, is classification of radiology. So here's an example of an X-ray. The AI algorithms detected there's some abnormality here, and arguably you could say there's some consolidation, and this is an early pneumonia. Some really interesting use cases now combining AI with photoplasmography, which I can never say, and that's essentially shooting lasers into skin and looking at the relevant changes in the light that comes back. And you can do that with some complexity. So combine vision with that with PPG, which is the same technology that if you have an Apple Watch, for example, that's how it reads your heartbeat, or a pulse oximeter, that's how it reads your pulse. It will give you the vital signs from a picture. So heart rate, breathing rate, and SATs. And again, this is technology that is live in the NHS today. Facial recognition, much more controversial, but if you ever open your phone using your face, that is a computer vision model and doing exactly that task. And skin, so dermatology, looking at lesions, taking pictures and recognizing classification of those tasks. And again, that is also technology live today in the NHS that people are already using at some scale. We've got predictive algorithms. So again, another example of deterministic algorithms. A couple of these ones are pretty famous. So a sepsis algorithm and heart failure. So what these models are doing essentially is taking a bunch of statistics, a bunch of metrics, similar to like the Muse score, for example, for sepsis, heart rate, age, white cell count, CRP, and creating statistical models that predict the presence or not of sepsis. And this is, I think there's quite a famous paper published in Nature a few years ago and deployed at a number of healthcare systems in the US. Here's a model for prediction of heart failure, looking at various predictors in various cohorts, looking at various features, for example, age, previous history of heart attack, sex, ethnicity, etc., and predicting the outcome in heart failure. These models are much harder, actually, in my experience, and did that a little bit as an academic, to actually utilize, because as good as they are diagnostically, it's not always clear what to do with the outputs or how you actually implement them. So funnily enough, from a product perspective, sometimes these can be quite difficult, but statistically, they are well recognized. And then we come on to other terms of AI that are becoming more and more ubiquitous. So when we take speech and we turn it into text, typically for these use cases today, transcripts, we call this speech to text AI. And you'll hear that term a lot when people talk about the space. They talk about speech to text technology. Older speech to text systems, voice recognition systems, were what we call phoneme based. So here's a bunch of phonemes. If you've got kids, you'll recognize this in terms of phonetics, but trying to recognize small pieces of the word, single syllables, then matching those phonemes to the specific word individually as close as possible. And that's how a lot of older VR systems work, and why they also took a lot of training and were quite prone to accents, and that would often make a lot of mistakes. Newer speech-to-text AI systems don't work like that at all. They take the entire context of the audio and then individually match each speech with the context with intelligence. So on the plus side, you get much more accurate speech-to-text AI accuracy. But on the downside, they're probabilistic. So there is an element of randomness even in the speech-to-text AI systems themselves, which you have to account for that. So some key terms, real time, you'll hear that. That means that the transcript appears as you speak. And batch transcription, that means you take the whole audio file at the end of whatever that speech is required to record, send that off all as a single file, and then we get the entire transcript back. It's slower, although actually not that much slower these days, but also it's actually more accurate generally because it has the whole context all at the same time of all of the speech. And then the way that we measure accuracy with speech-to-text models is something called the word error rate. You'll see that if you look at any reports for accuracy and safety of speech-to-text AI. And that just literally means you have existing transcript that somebody's validated, normally a human being. You run it through the speech-to-text AI system. It gives another transcript. You just match up where mistakes were made, and you call that the word error rate. And again, that's something that's been falling continuously over time. Now, large language models. So you've probably all, if you're even adjacent to the space at the moment, come across ChatGPT, or to mention some other vendors, Anthropic's Claude, Google's Gemini, Facebook or Meta's Llama, for example. These are all large language models. And this is where we delve really into probabilistic models that have an element of randomness. Now, large language models are transformers. Transformers were designed to transform text from one form into another. And actually, they were originally designed for machine translation. But the way that they work, they sort of predict the next word. And then there was a finding that actually by doing this, you actually put knowledge into the model. So to write a sentence, you have to have some representation of knowledge because that sentence has to make sense. And that sense contains knowledge within it. So a typical sort of use of one of these models is text plus or minus an instruction, and that's what we would call the prompt, passes into the model, and then new text is output. The terms that we use for the input is prompt, and that's normally like an instruction plus potentially some other information. And then the output is what we call inference. So you might hear with lots of AI models the inference, which means that the model's inferred some sort of meaningful output. And often we'll talk about inference time, or the data processing and inference is a bit different. And I think this is most important of all. So these models were designed to output something that looks like, and this is the critical difference, that looks like an accurate answer. But they aren't trained that that answer is factually correct. And that's really, really important because sometimes these models will have the capability of what we call hallucinations. The model will make things up in our parlance. So the model's perspective, it's achieving what it's asked to achieve. If you asked it to give 10 references for some sort of legal case, it would give you 10 references. But the likelihood is those references do not exist. So using large language models as knowledge bases still has these inherent problems. It's not actually what they're designed for, even though it is a byproduct. And even though it gives really good understanding and context, it is not the fundamental purpose of these models. Now, getting a little bit into the future state, but I think it's useful to talk about what other types of models are coming online now. So we use the term multimodal, which literally means different types. And we see that more and more. And all that means is you have a unimodal model here, like text that outputs text, a multimodal model you can put a text, an image, a video now actually as well, documents, and the AI model can process that all together and then output a single output. And the output also can in fact be multimodal. You can have image to image, image to text, text to image, and this is a very interesting time to learn the nomenclature. Here's an example to be super concrete. So here's a picture, and you put some text in. Tell me what this is. So that's multimodal model. You've got an image plus some text, goes into the transformer model and outputs a text output. This is the Eiffel Tower. And that would be a type of multimodal model. The reason it's important to understand this is like people are now thinking about using multimodal models in healthcare, for example. My inherent distrust of that is that actually it's much harder to tease out which part of the model is doing what, and therefore to improve it, and therefore to create safety cases, etc. And I think that's something that we'll have to figure out over time. And lastly, on this sort of run through AI as it is today, knowledge bases. So there's a technology called retrieval augmented generation, or RAG. And what we're doing here is we're taking data, so actual knowledge, and turning it into numbers, which we call vectors. And then we'd make that searchable for a large language model. So to solve one of the problems of large language models, which they don't necessarily have verifiable data, here's a technology where you take a bunch of structured data, or in fact unstructured text, turn it into a bunch of chunks of that data, turn those chunks into various numbers, and the math of that escapes me, so we can talk about that, and I'll send you some resources on how you do that. And then the model can search that very quickly and then utilize it in its response. And this, in theory, should increase the factuality of the outputs of large language models. In practice, still has some problems around hallucinations and omissions in the same way. And it's another thing that you need to learn to evaluate. Some other important terms on our trip through orientation then. So how these models work, right? They run on very high-powered computers, typically GPUs, and we need to use that technology to perform them fast enough in real time. But obviously, most of those GPUs require large data centers. They get very hot. It's just not practical. You can't run most of the top-of-the-line AI models today on your computer at home, although increasingly that is changing. So generally, these computers are accessed by the web, and we call that cloud compute, and most of you will know all about this anyway. Or they can be installed locally, which we call on-premises. So typically, on-prem refers to something literally physically located on-prem, or within the data structure that you already have, and data doesn't have to leave, which is the crucial piece. But generally, cloud is required because most companies, most places won't have access to the GPUs that they need. The other two terms that are really important at the moment are open source and closed source. So open source AI models literally means you can download the model, and if you have the expertise, you can run it on any system that you want and do pretty much anything that you want with it. They often come with licenses, so you can't legally do anything that you want with it, but in practicality, you can. Often that's cheaper, but it depends on the use case. And actually at scale, you still need the hardware to run it reliably, to have the enterprise grade. So often actually doesn't work out cheaper at large volumes. And then closed source is where you're accessing models via companies. So OpenAI, Anthropic, Google, they're all hosted on various cloud service systems, AWS, Microsoft, Google, etc. And you can access them anywhere. Generally more expensive. And then you have to get into data agreements as well around hosting and bits and bobs. So there's pros and cons, and there's not really, in today's world, a good answer of where AI should run. It's just about managing the different systems. And again, really important to ask vendors where their models are sourced, how they're trained, who trained them, who looks after them, and actually what the enterprise agreements are if it's closed source models. Okay. So let's have a little breather there, because that was definitely a bit of a gallop. Oh, it's called Tortus Shell. Sorry, I'm just looking at the chat now. I've been switching back and forth. That's actually very useful. Thank you. Thank you so much for that. Okay, so what we'll do now is just for a little bit of a break between the question and answer time, and just see how many of you are actually listening to anything. We'll do a quiz. So, he says, not knowing how a quiz. Yes, here we go. So for this webinar, the purposes of this webinar, where's the definition here? Yeah, so let's publish that. Publish poll. So if you see in the polling side, can I push this to, I don't know how to do that. Oh yeah, great. So people are voting. So I'll give you about 3 or 4 minutes to have a vote on that while I see actually how many people turned up to this. Oh, 41 people. Okay, great. So we'll give it a little bit of time. We've had a few different votes. So yes, for this webinar, what is the Tortus AI definition of intelligence? So like, yes, there are many predefined definitions of intelligence, but what is the one that we're talking about today? Because that's basically how, for this session and for all the future sessions, we'll talk about AI around and in around that sense. Give you guys a few more minutes on that. Yeah, it looks pretty good. So I think generally people are agreeing that we're defining it as the ability to solve a problem. And again, we talked about the speed of the problem and the intelligence, and it did seem that we had some pretty impressive mathematicians on the call with us. Okay, let's answer the next question. So again, for the definitions that we've used today, what is narrow artificial intelligence? Is it narrow bandwidth cellular AI? That's cool. Is it low latency AI running locally? Or is it solving very few or only one problem at a time? And can everybody see that okay? It's a slightly different poll. I could unpublish the other one, so that's easier to see, isn't it? No one's voting. Can you see the poll okay? The second poll? It's the same technology. It may not switch over as easier actually. If there's anyone. Oh, people are upping it. Yes, we can see it. Okay, great. So let's let people vote on that. Oh, I can't see that. Oh, I can now. Sorry, yes. That's my fault for not using the system well. Yeah, great. So solving very few or only one problem. Not a super useful definition, especially as we're moving to very complex models, but certainly something to understand a bit more about. Okay, so an AI model being trained means what? It practices with a human tutor. It gets better at solving a problem using data, or it attends a special AI school with other AIs, which sounds like a great TV show. We should definitely watch that one. Yeah, great. Okay, people are voting for that. Gets better at solving a problem using data. Yeah, I mean, I'm not saying that these are difficult questions. It's just it's nice to consolidate knowledge at the end of a session. Okay, great. So AI models can make bad predictions when given too little data, given a lack of diverse data, or all of the above. Yeah, most people going for all of the above there. And that's exactly right. So we talked about underfitting, we talked about overfitting. I guess one of the other answers here is like given the wrong data, and you certainly see that in different models, and that's one of the biggest complexities. One thing I didn't mention actually was there's a sort of slight misconception that more is better with certain AI models, but actually training data that's poor quality often actually decreases the quality of the model. So quality of the data, and often having people like do hand analysis of it, which is pretty grim, often is the key to producing really good AI models, as opposed to just slamming in a bunch of quantity. Obviously, ChatGPT has got the whole internet behind it, so that's a different example. Great, yeah, all of the above. Good. AI ingesting images and outputting a classification is known as what? Computer vision, visible working, or AI? I really enjoyed that one. Maybe too much. Yeah, people are enjoying computer vision. Good. Visible working is always a bit of a joke. Yeah, people liked AI. That's good. I thought that was quite fun. There's a whole company name in that, I think, AI. People have missed a trick there. Some people have put invisible working. I like that. I like that for risk. I do think in the world of an AI is monitoring all the situations, visible working will be one of them. And maybe there's a a dystopian future there where AI is used to see if people are visibly working, but that is not something that we are doing today. Great. Okay. And last couple now. So first of all, we didn't actually mention this. So this is maybe a test a slightly off piece to see how well people know the space. So ambient voice technology combines what types of models? Image to text and computer vision, speech to text and large language models, or text to speech and multimodal models. Now, when we talk about ambient voice, what we mean is listening to consultations and creating notes and letters. So out of the model types that we've looked at today, which of those models will sort of fit that technology? Is there imagery in there? Is there multimodal models? Yeah, most people have gone speech to text and large language models. So image to text, we talked about a little bit with the picture of the Eiffel Tower. Computer vision, we talked about. Text to speech, you'll see models like 11 Labs and a couple of these others where you write some text and it will generate voice for you. I think that has its place certainly in healthcare with sort of agents and a number of different translation tools maybe down the line. But today, yeah, most people have got it right. It's a speech to text model that takes the audio, turns it ambiently into a transcript, and then that transcript is summarized to make the downstream documentation and other tasks, potentially like clinical coding. Okay, last question before we get to the Q&A, and well done for getting this far. So last but not least, knowledge bases, just unpublish some of these, can be added to LLMs by using A, RAG, B, OCR, or C, SVM. And I didn't explain what SVM is at all, so I won't ask anyone to explain what that is. But I think most people are getting, that it's retrieval augmented generation. OCR is optical character recognition. So that's the type of computer vision we use to read letters, so characters. And that's also obviously very useful for healthcare where we're reading documents. And SVM is an algorithm for training models. It's a support vector machine and completely slightly red herring. Yeah, very good. Okay, awesome. So you've come to the end of the first session of the AI Academy. What is AI? And I feel hopefully that maybe there's 1% increased clarity, if not more. We've got some other sessions coming up, beginning of January into February. How to evaluate AI in healthcare is the next session, and we'll go quite deep on the various model types, how to evaluate them, accuracy, what you should be asking vendors. The session after that is about understanding clinical risk. It's a really interesting area, constantly changing. Also managing things like bias, diversity of data, how you're accounting for various use cases, thinking about product, not just about technology. Beginning of February, we'll look at driving adoption. How do you get, you buy expensive technology is a problem that we all have across the NHS, but no one wants to use it. And what is that adoption gap? What is the trust, the credibility, but also the training and the requirements for implementation, which actually shouldn't really be underestimated. And the last session, I think we'll go a bit crazy in the middle of Feb, is to talk about the future of AI in the NHS, the future of technology, and see where we get to from there. Great. Okay. Well, we've got about 10 minutes before we finish up this session, and thanks so much for your engagement and your continued attendance. We'll go for some questions. You can either ask them in the chat, or there is like a little questions tab as well, where you can just send questions directly. And yeah, well, if there's any questions to answer, now is the time to ask them. And no one's asked anything thus far, so let's have a wait and see. I can see people are typing. Oh, someone's managed to make it into questions, so first come, first serve. How to arrange info or a demo of your product. Oh, that's nice. Yeah, so you can go to app.tortus.ai, or in fact, my email's on the next slide, dom@tortus.ai. And yeah, we can arrange that with the commercial team for sure. I'm just using this platform for the first time. Dom Pimenta is live answering. Oh, cool. Okay, I'm done answering. Yeah, I'll put the detail in the chat. Great. Okay. Any other questions? Oh, another question. Can you discuss how data security is considered for both open and closed models and cloud-based systems? Yeah, that's actually a really good question. And it's very much dependent on, first of all, where is the data going? So I think the way to think about that as a question space is to really look at the workflow for whatever the data system is. So if you have some data in your hospital, and whatever the vendor is, whether it doesn't really matter in terms of open or closed source, they will have to probably send it somewhere unless you're hosting the GPU locally. So it really is like, where does the data physically go? And then first of all, mapping out the data workflow, that is the most important part, because you'll find all the different vulnerabilities. So if you have to transfer the data to a cloud, who's the cloud provider? Is it someone that's recognized? Are they based in the UK? Are they GDPR compliant? Do they have the various ISO, GDPR, things like that? The second thing to answer then is like, when that model goes there, what is the model it is running on? Is it a model that's licensed from another company, or is it an open source model that they're running on that GPU? Obviously, if it's not going outside the cloud, if it's staying inside your system, then data security is as secure as the GPU is in your data environment. And also just think about like, what is the flow in that cloud environment? Does it go to multiple vendors? Does it go to one vendor? And really like studying each part of it. And also asking some questions like, at every stage, not just the flow total, but at every stage, is the vendor taking super careful care on, does that data with potentially patient identifying information need to be exposed to each of those models, or can you actually remove the data at some point in the flow, put it back in at another point in the flow without affecting overall performance? So I think it starts with data workflow. Open and closed is not so important. I would say a little bit on the open side, data security is down to the cloud provider. On the closed side, if it's a big company with an enterprise zero data retention agreement, you can see those agreements, pretty straightforward, but it's going to be Microsoft, AWS, OpenAI, one of these similar ones. And then also some assurances from the company themselves that they're not training data, and if they are, they're declaring it, and you're needing patient consent. Hope that's useful. Okay, we'll keep going through these questions. Great. So Adam Smith says, do you have any recommended resources, courses for clinicians? Resources, courses is quite nice. To learn about AI and how to implement locally. Yeah, I'll share one. But the one that I did actually to start with was the Coursera course with Andrew Ng, Ng being NG. That's excellent. And it's really pitched a layperson introductory course. You have to be somewhat techie, but it will teach you also a bit of Python, so you can go through that. There are more courses now on large language models and some other resources. And I'll have a little think about, the levels of healthcare resources. There are a few academies. The RSM runs a really good podcast with Dr. Annabelle Painter. That's a great place to talk about the space in general, capabilities, the future. Health tech podcast as well, also an excellent resource, because you'll often hear about how things work, and it gives you an overview from the people building it. Yeah, we'll share a bunch of resources after that one. And then how to implement, yeah, I think that's actually a different track entirely, and something that we'll probably cover in the next couple of sessions about deployment and evaluation. Great. Naomi asks, do you have any advice for medical professionals in the process of creating an AI product and looking to connect with technical partners who can help with product design? Wow, that is a really good question. Do I have any advice? Yes, I think one thing is, don't forget that you know what the problem is, right? I think that's something that we forget sometimes as medics, is that it's our problem. We understand it inherently. It might be super obvious to us that like the handover sheet, for example, is inherently dangerous, it's wrong. It's not actually that obvious to anybody outside our field. So in medic land, as we all know, if you're married to lay people, for example, it's actually quite a weird space. And some of the rules, some of the unspoken things that we do, some of the things that we do subconsciously every day are not at all obvious to non-medics, to people outside the industry. And that specifically is with like engineers. So the first thing I say is like, make sure that you understand the problem. And the best way, there's a phrase in one of the books that we use here from Basecamp, says build uphill. And what it means by that is like you should build your way into finding these solutions. So the one thing I'd also recommend is if you can't code, go and learn to code. Or if you can't, you know, if you can't visualize it, draw it. Or like whatever you can do to take your idea as it is today as far into the future of realness or testing it as possible is really important, because that will help you on product designers massively. And then the flip side of that, to play devil's advocate with myself, is like we all think as clinicians that we know how to do it, and actually I've learned specifically at Tortus, you just, there's so many other use cases. People are doing things so many different ways. So as soon as you've got an idea that you can show someone, go and show it to a colleague, because again, that will make it much richer. And anyone you work with on the technical side, whether it's product designers or engineers, they will also want to hear, well, how many people did you test with this? This is just your idea. Because also actually in the real world, that doesn't go super far. And then sometimes also just make sure that you have a great solution, but just understand that, do you understand the actual problem? Is this solution suitable for the problem to solve it fundamentally, or is it in fact a solution that solves your specific problem but doesn't generalize? Because again, it might not be worth even building it or using something off the shelf. And the last thing I would say in terms of where to find these people, hackathons are really good. There's quite a few in London now where a bunch of engineers interested in the healthcare space, a bunch of AI scientists will turn up. They're always looking for clinicians. It's a really good place to start products. Tortus was founded in an accelerator, entrepreneur first. You know, myself and Chris Tan, my co-founder, machine learning engineer. That's where we met, and then actually, you know, became the company as it is today. So I think that's also another really good place to look. Okay, great. Got some more questions. How does the UK compare as a location for an AI startup? Have you considered listing in the US? Oh, that is a good question. Yes, of course, we've considered listing in the US. I think I'll tell you a story. I think so for startups specifically, forget AI for a second. I think that's a different question. I think the difference between here and the US is like if you go to someone in the US, you're like, I've got this crazy idea, I want to build this thing. They'll be like, yeah, man, let's do it. And in the UK, they go, oh, I've got this crazy idea, I want to build this thing. And they'll be like, nah, I can't do that. So it's a bit about ambition. It's a bit about optimism. It's a bit about our view of failure. I think it's just a cultural thing. Like if you go to someone in San Francisco and you're like, I've got this cool idea, I want to build a thing. He's like, yeah, I'm going to quit my job and I'm going to build it with you. Because they've seen what happens when you join Facebook as one of the first employees, or you join Google, you know, and that culture exists there. And that's one of the bigger problems that we have here is like new ideas are sometimes harder to get off the ground. Now, having said that, the UK and the NHS specifically is actually a great place for an AI startup. Loads of innovation, loads of people super keen to actually like help patients. In the US, the incentives are crazily misaligned, and for healthcare specifically, probably not actually such a hot place to build. But then again, there's differentials on that. Talent, once upon a time, engineering talent, very popular in the US, actually very expensive here. London is now becoming a great place for AI talent. We've got DeepMind, we've got Google, we've got Meta, we've got Anthropic opening soon as well. Paris also really good for AI talent. So actually the UK is becoming a really good place, specifically London. With the European regulations, you have to keep an eye on that because that might change things again. But at the moment, it's just about, I guess, have a big idea, find people that really have the big idea as well. Again, accelerators are good for that culture. And then everything else here is actually a really good place to build, and can talk a bit more about working with the NHS because it's been really good for us. Great. Can you please repeat the name of the Coursera course again? Yeah, it's called Introduction to Machine Learning, I think. It's with Andrew NG. So I'll put that in. Sorry, I'll put that in the chat because I've answered that question now and I didn't mean to do that. Okay, and I've got some nice comments. Simon Brunner said a great session. Oh, thanks so much. Adam Smith said, do you have any recommended courses? Yes, I will send that in the chat. Thank you very much. Awesome. Well, we're coming to the end of time. Any more for any more? As anyone, as I used to say when I was a waiter a long time ago, any questions for anybody else? Awesome. Well, I think it's just people being very nice, and that's always appreciated. So as I said, we will be running these sessions every couple of weeks, with the exception of Christmas Day. And the next couple of sessions will be joined by some of the team here at Tortus. So there's 5 clinicians here as well as some scientists. So look out for some co-hosts, and I might make it a bit more exciting than just me talking for a good hour. And we will come back to it again soon. So thank you all so much. And yeah, and the recording also we will be sharing around. I will leave the chats and comments open for any residual questions that people wanted to ask off the bat. Yeah, have a lovely Christmas, and we'll see you in the new year.